maybe I'll start slowly, yeah. So there will be several topics, so I will a little bit change what I wanted. So I will speak about oscillatory media, and then about common noise, and then in the last part, I will try to combine these two ideas of synchronization by coupling, what I introduced last time, with synchronization by common noise. And there will be, in our opinion, quite interesting, a little bit even counterintuitive interplay of these two types of synchrony. But first I will maybe shortly speak about oscillatory media, because it's a very natural thing which physicists like. So if you have some elements, you put them on a regular lattice, and then you look, so what is happening to them. And indeed, in many cases, you can generalize an ordinary differential equation which describes some maybe oscillations with something like diffusion, because quite typical it is for chemical systems where just chemicals diffuse, maybe with different diffusion constants. Or if you put these chemicals in some compartments and there is some exchange of them between the compartments, then it will be equations like this, where X is a concentration in each compartment. And quite in a spectacular way, recently a group of experimentalists in Technion at Weizmann Institute in Israel, they were able to produce many also non-trivial lattices, planar lattices of lasers. They start with a relatively large laser plane, and then they, on this plane, they, how to say, delete all the space except for some dots, and there is maybe so several hundreds in each dimension, so it is some thousands of these dots, which can be organized in a very different manner. So what they call, so there is a triangular lattice or spiral lattice, so they just put somehow trafaret and then make it. And so all these lasers, each of them, it is an oscillator, and they are more or less identical because they are made of one, how to say, plate. But interactions can be different, and they also try to reproduce some lattices which are quite popular in the solid state physics. So when you put spins there, but they put oscillators there.
Each point is laser.
Yeah, so they claim at least. So it is independent, so in principle, of each other. So each point, okay, so here you see, so there is maybe several hundred of them. It is lasing element. And they claim, so it is basically coupled to the neighbors, and they can make also global coupling, so they really play with it. Yeah, and then, so, okay, so here you maybe hardly see, but this is, so they have a series of papers where they study different properties here. Sorry?
Are they shining in this fashion?
No, but you see, so you first prepare your laser elements in such a manner, and so here you see that these dots are emitting light. Okay, so maybe not so good in this projector, but really, so each dot here, so you see, so you have a spiral, it consists of small dots, like here, and each dot is each individual laser, so it is coupled to its neighbors. Yeah, and they can see what is the phases by the far field where you sum all this, how to say, where they you observe interference as a summation of all these elements. Yeah, so here it is triangular, here it is this, what is called Kagome lattice. hexagonal. Okay, they claim so that they do, and this is real experiments. The purpose is so that they say, okay, so in solid state physics you have these ideal systems, and we can model them just and observe whether it will be some frustration, for example, here, if you have some repulsive coupling. So here you can put, if you have repulsive coupling, you can put phase pi here, 0 here, pi, 0, it will okay. It's more or less like one-dimensional. It will be like chessboard structure. And here on the hexagonal lattice, you also can have so that neighbors have pi, 0, pi, and so on. But on this lattice, you cannot. On triangular lattice, you cannot do this. You have frustration. So you cannot make your all neighbors to have, so if it is 0, then you cannot, if you hear pi and this pi, so they will be repulsive. So that will be something else. And they claim so that they, with this, solve some, how to say, minimization of some Hamiltonians that also appear in the interaction of, say, spins on such lattices and such networks. This is their, what you read in their papers. So they just use this as some tool for the modeling phenomena in solid state physics, dynamics on lattices. Let's just show this example, what sophisticated lattices you in fact can prepare. Now, if you now try to do so, what could be some simplest equations and phenomena here, it is the following. So you have to put on each side an oscillator. And here, so frequency is not present because I'm already in some kind of rotating reference frame where this frequency. But there is a complex amplitude. So this describes one oscillator, this element. And then you put some nearest neighbor coupling with some complex coefficients. It's generally, it is complex, yeah, because it's complex amplitudes. This is so-called Ginzburg-Landau equation or complex Ginzburg-Landau equation, which is in this field, just this name. And as before, you can make a phase reduction in the sense so that you assume, for example, that this C2 and C3 coefficients are small, so you have some separation of time scales. So you have slow dynamics here and fast relaxation to some constant amplitude, which is 1 here in this equation. And you basically assume that this amplitude is constant, and this is the phase reduction in this case. And you end up with phase equations for the nearest neighboring coupling. And this equation is just generalizes Adler equation for the nearest neighbors. You have here just phase differences to the right and to the left, but you can also have a cosine term. Generally, you have sine and cosine from this. And if you go further, I again rewrite it, so you can see where the sine and cosine come from. So C2 is a real diffusion constant. And so positive C2 means real diffusion. So it will be equation for close phases like this. So it tends to equalize them. But if it is negative, it is, so to say, negative diffusion. And it means so it makes phases, it is repulsive coupling, it makes phases opposite, so 0 and pi, and it will give you chessboard structure where the nearest neighbors have such phase shift. So it's just the case of pure diffusion, either positive or negative, leads to some, I would say, stationary pattern typically. It's possible also to have some, how to say, waves, but it's not so, okay, so it's also possible, but I don't go into details. But on the contrary, if you have only this term, C3, you have a cosine coupling, where it's purely cosine coupling, and it is an interesting situation. You get essentially a Hamiltonian system. So this system of these equations, it doesn't look like, from the first glance, Hamiltonian, but it can be written as a Hamiltonian one. So it's a system without any dissipation. And this is somehow interesting, in my opinion, situation. You start with a very, how to say, dissipative oscillators. You couple them in some conservative way, but when your dissipation goes to infinity, so in this limit, you are left with the phases for which there is no dissipation at all. So what remains is purely Hamiltonian equation. So this is just a Hamiltonian equation on a lattice, which generates waves, and these waves are quite interesting. There are so-called compactons. You maybe know so that in nonlinear lattices, they quite often have waves which are called solitons. It's localized waves, yeah, which can propagate and interact, look like particles. Here, there is some special form of solitons, or solitary waves, which are called compactons, because if you try to linearize this, you can write it in this way. If you try to linearize this equation for small v, you see cosine start with a v square. So if you linearize, you get here nothing. So it will be 0. So there is no, in this lattice, there is no linear waves. Yeah? So it is a pure nonlinear objects, and therefore they don't have exponential tails, but they have super exponential tails. They're really very local structure. So in the continuous, not limit, but quasi-limit, they even have a finite support, because equation will be degenerate, the corresponding. And just, you see, so, but the system of equations is very simple here. You just put it on computer, this equation, just whatever. It calculates you such a, you have initial condition, and then this, how to say, solitary waves propagate and have very interesting properties. There is another example, yeah? Yes, yes. So these equations are, how to say, so I would say, so this equation, which is purely Hamiltonian, it appears from this equation in the, say, in the limit, asymptotic limit, when you don't have this term, and you put here, okay, suppose you fix here and you put here some coefficient. If this coefficient goes to infinity, so then in the leading term you have this. So it means so that your, how to say, amplitudes really are frozen like this. Then it will be exact. But of course, so there will be corrections 1 over this coefficient, yeah? But the limiting case, you see, so you start from dissipative objects, you couple them in a conservative way, and when dissipation goes to infinity, you restore some kind of conservative dynamics. So this appears for me a little bit maybe worth noting as an extra. Now, I don't want to review here the full, how to say, variety of different wave patterns which people observe here. One of the typical So there is reviews and maybe even books about complex Ginzburg-Landau equation where you put also additional terms, and in 1, 2, and 3 dimensions there is turbulence there, there is spiral waves, a lot of effects which appear in this equation. But the basic ones are, okay, so synchronization for dissipative coupling, and I would say another interesting limit is pure conservative one. So there is so it's a huge field of research. So you can put lattice, you can put medium as a partial differential equations. A network, it's like a disordered lattice, so you can put there, and there are many effects of special temporal patterns. Sorry, again. Yeah, it's either what you want. You can take a value, but you can put them also on from 0 to 2 pi. It just depends on what you want to see, what you want to observe. But you see, so it's easier to consider this really on a circle, then you don't have any explosion or something. Now, you see, for example, if you write the following equation, yeah? So it is also an interesting equation, but its solutions can explode. Because quadratic equation, so some solutions can go to infinity in a finite time. But here on the circle, so nothing happens. So if you have a compact phase space, so n-dimensional torus, solution is there. So it is easier to look at on this as a solution on a circle. Okay. Now, I want to somehow shift a little bit the topic, but it will be from one side, it will be less dynamical, but it will be more stochastic. And I want to describe synchronization by common noise. Yeah? So, and then we'll apply, so combine this with what we learned about synchronization of oscillators. So here, the basic effect is the following. Suppose you have two systems, and here I write just discrete, so to say, stochastic maps, and then later it will be stochastic differential equations, but here it is easy to see the effect. Suppose you have a discrete time system where xi is some random sequence of random numbers, but two systems which are identical, so function is the same and the noise is the same. And what differs are initial conditions, x and y. Yeah? And the question is, so what will happen with this x and y in time n, in discrete time n? Yeah? I will give them examples how it looks like in physical, but here it is just a mathematical question. Now, it always, such a situation, such a system has a fully synchronous state because of symmetry. If x is equal to y, it is a solution. Yeah? And it is, so to say, invariant state. Yeah? So noise doesn't perturb it. And the question is whether this state, let us ask the first question, whether the state is stable or not. Yeah? So it means so that we consider a situation where there is x equal to y, there is the state, and we make a small perturbation of it. So two systems are really close to each other but have some difference. And then for this difference, we can linearize these equations and have this. So this difference obeys such a transformation if we go to the logarithm, then it will be just this equation where you see so that z is in fact, how to say, Brownian, performs a random walk with such steps. Yeah? And then it is clear, so if you have a random walker, then depending on the average value of this quantity, z will on average grow or decay, or go to plus infinity or to minus infinity. And the condition, so we have to calculate the average of this logarithm. And this is nothing else as the Lyapunov exponent of the dynamics. It's how the Lyapunov exponent of the system is defined. And so if it is negative, if you have negative Lyapunov exponent, it means so that z will go to minus infinity, and this means so that this difference will go to 0. It's like stochastic stability is also defined for linear systems. Yeah? But this will mean so that two systems driven by common noise, they synchronize. So you can say, yes, there will be synchronization, so 2 or more, so there is no any restriction. We started with 2, but you can, any number, started from different initial conditions. Now, still, you see, so I here assume so that if the state is stable, so then it will eventually appear. So this needs some additional probably proof so that indeed you can start from any initial conditions and be attracted there. I'm not sure that it might be in some situations you can have bistability, but this is difficult. But say in most situations it is the case. So you start from different initial conditions, and they will essentially evolve to a single state which somehow is following this noise trajectory. But you can have also desynchronization if Lyapunov exponent is positive, and you prepare these states of the system close to each other, but they eventually will diverge. Now, there is some kind of, so I suppose that the theory of such systems in mathematics was originated by Baxendale, and then many people around, so Ludwig Arnold also contributed. It's Crowell, for example. And now I suppose, so there is some generalization. There are guys at Claude and Rasmussen, so they also do in this direction. But yeah. Now there is one thing, so is here important to take care. So if you put two systems on a computer, it might happen that they will synchronize not because Lyapunov exponent is negative, but because numerical precision is insufficient. Because on computer, if you have two identical systems and they come close together, so distance smaller than numerical precision, then there will be exactly the same representation in the computer, and so all evolution will be the same. So they will just merge, although it might be that on average Lyapunov exponent is positive. So one should be aware of this. Now, it's interesting to observe the following. If you just observe one system, so the recipe is, so you have a noise-driven system, you calculate the Lyapunov exponent, and depending on its side, you decide whether you have this or not. But if you observe just one system, you cannot recognize it. So just from the process, it will have the same random properties for negative and for positive Lyapunov exponent. You cannot tell just from observing one system whether it is will synchronized or not. you need to make a clone of it, or, I don't know, twin, with other conditions, initial conditions, and then look how they behave. But just from one system, it will be disordered in both cases. Yeah? So also, you can put not necessarily noise as a driving force. You can put also, for example, chaos, deterministic chaos. So it will be a skew dynamical system. We have chaotic system, and then drives another one. So you see, okay, so driven system behaves randomly. You need to make a clone of it to see if these two systems move together or differently. Then you see whether it is a positive or negative Lyapunov exponent. Now, there are, yeah? No, okay, so if you have many systems, so if two systems, okay, so if you have two systems, so just as a function of time, and they eventually will come and together, yeah? So now if you have many, it will also happen. So you look on the, so, and here the variance in this ensemble will be just 0. So instantaneous distribution is here. So at this moment of time, I start with a, how to say, 100 different systems, and I see that they are all in the same state. So the instantaneous distribution is a delta function, essentially. It's a point distribution. Now, there are several experimental realizations of this, which are quite maybe interesting. One is in neuroscience. In neuroscience, there is the following problem. So neuron, in some cases, it is an oscillating unit, but in other cases, it is not oscillating, but it waits for some input to produce a spike. And it responds with some spikes on the input. Yeah? But input is not something regular function. It's typically a sum of inputs from many other neurons. And if you measure this, so these inputs look like some random function of time. Yeah? So it is quite, you cannot recognize any pattern there. And now this input acts on the neuron, and it produces spikes. And then the question is, which you can pose, does this neuron really only follows the forcing, or it adds to this forcing something else of its own dynamics? Yeah? And they described this due to Meinen and Sainovsky in some 97. They described this as reliability, and they suggested the following test. You take the neuron, you add on it with a noise, so this is, and you repeat this experiment several times with the same, exactly the same noise. So you record noise on a computer, have a neuron, you put this noise as an input, you record a sequence of spikes. And then you repeat your experiment with the same neuron, with the same noise. So the only thing you cannot control are initial conditions. But then you see, so here, this picture, so it is overlap of, I suppose, 10 experiments, 10 trials. And this more or less is just corresponds to this picture. Yeah, so it is like you have 10 identical neurons, and you put common noise on them, and you just look, it is the same response or not. And you see, so here there are some regions where it is really very, overlap is very good. So it is like here. And maybe there are some regions, in the beginning especially, when the overlap is not so good, and maybe here due to some reasons. Yeah?
You're saying are there 10 trajectories?
Sorry?
There are more than one trajectory?
10 overlapped, like here. 1, 2, 3, 4, but they overlap 10. No, here 10, I suppose. Here 10. No, this is this experiment. So here 10, and I suppose they do this even with one neuron in vivo. They don't even take it from the organism. They just put electrode, and it is still in vivo, and they put additional, yeah? Now, there is also another way. It is here. So a similar experiment, it's another representation. So you don't overlap them, but you detect spikes, and you put the spikes as a small vertical intervals, and there are 25 of them. So here there are 25 trials. And you put them in this way. So just, you see, so here there is this vertical. And this is the noise which they use. So here it is a very strong noise, and here is a small, and probably this noise is taken just as some realistic signal in brain, which may be of this type. And you see, so that there is a pieces where this synchronization is not so good, but here it is vertical lines, means so that neuron answers exactly the same, which you can hardly predict. So when you look here, so where it will be, but there is this, so this property there is called reliability. Yeah? And this is exactly this synchronization by common noise. Sorry? No, you just can see. You can decide yourself. Yeah, so this is the noise which they apply. This is the applied noise.
There is from noise up to time 1.
Yeah, and then a weak noise. But nevertheless, you see spiking. So here they are reliable, and here reliable. Here there is a little bit less reliable. Then here maybe not so reliable, but here again becomes reliable, and here again less reliable.
But I'm not sure what to extract the qualitative level from.
Oh, you can then, okay, so this is just qualitative observation. Then you can decide, okay, maybe the stronger noise will lead more reliability. For example, so now, okay, so I'll come to this a little bit. So you take your favorite model of a neuron, you put some noise, and then in the theory you can calculate Lyapunov exponent, and you can decide, okay, so there is some optimal noise intensity or some other characteristics for which Lyapunov exponent is maximally negative. It will be then the best synchrony. And maybe it will even become positive at some point, so that neuron will be no more reliable, but will add some its own dynamics due to this positive Lyapunov exponent to the as an output. Yeah. Now there is another experiment or a situation which is a little bit in this direction, although not so perfect. You see, so if you think about population dynamics, then if you have two independent populations, for example, so they measured sheep populations on 2 islands near Scotland, where you know the sheep they don't swim, yeah. So and there are no humans there, so there's just sheep. They live there on their own, and then scientists come and, I don't know, maybe even with helicopter, and count these sheep all the years for this more than 30 years. And the idea is in this biological, how to say, population dynamics, that there are the same weather conditions, of course, on 2, and this is like common noise, because weather is random, but it is the same on these 2 close islands. And there should be also some correlation in the population dynamics. Although you can hardly consider this as a two-dynamical system. It's not as clean as, but at least there is such effect in population dynamics. And maybe the last example, which also you can do experiment, is the following. Suppose you have a fluid flow. Yeah, so you have a fluid flow which is some field, yeah, which depends on space and time, and this is some kind of regular field, so some kind of turbulence, maybe well-developed turbulence or not so well-developed turbulence. Yeah? And now suppose you put different particles in this field and look on their evolution. So the dynamics of these particles, so there are many of them, it will be like this. Yeah? So it's exactly a population of different, particles in the same field, which is a random function of time and space. Yeah, it's same turbulent field. So then you can ask whether this, so it is so-called Lagrangian dynamics. Yeah. Now you can ask whether you expect some negative Lyapunov, largest Lyapunov exponent. Now, if you have incompressible fluid, then the Lyapunov exponent cannot be largest, cannot be negative, yeah, because the sum of Lyapunovs is the phase volume contraction, and it is zero, so it is, you really expect something positive. So it means that your particles will be dispersed, even if you put them all together. But there are situations where fluid is highly so its divergence of fluid is highly compressible. It is the following situation. Suppose you have a pot of, say, some liquid, and the particles can only float on the surface. Now, the flow on the surface, so if I put only this two-dimensional flow on the surface, now let's put S, it will be, it can be, there is no restriction. It can be highly compressible. So for example, suppose you have one vortex, so then on the surface, all particles are compressed to the center. So, yeah. So if on the surface, so you can have, it's not divergence free, and then it's depending on how this flow is organized, you can have negative Lyapunov exponent. It means so that you put spread particles on the surface, and they will eventually, say, garbage on the ocean, which is fly on the surface, and it will form a cluster, or several clusters, because it is take too long. Yeah. So all garbage will be together because this will be they will be synchronized in this sense. Now, it can be also positive if you have steering in this direction, and that will mean so that your attractor will be not a point, but some random fractal. But still, it will be some concentrated, and garbage is not spread over the sea surface uniformly, but it is concentrated on a set of, say, low dimension, either maybe points if largest Lyapunov is negative, or if it is positive, it will be some fractal set dimension between, say, 1 and 2. Yeah? So this is another. Okay, now let us think on the following. Suppose, so generally, if you have a nonlinear system, so Lyapunov exponent can be anything, so you have to calculate it. You can hardly say. Now, you can think, okay, but where I can really have a good estimation, it's the situation of weak noise. Then, if noise is zero, the Lyapunov exponent will be just that of the, if you really consider it some kind of non-singular situation, then the Lyapunov exponent will be that of the underlying dynamics. So if you start with chaos and add noise, so then it will remain chaotic. It means so it will positive exponent will remain positive. Okay. Now, if you will have a stable system, if you have a stable fixed point, largest Lyapunov is negative, you add noise, you also, small noise, you expect it remains negative. Now, the only non-trivial situation is of periodic motion because it has zero Lyapunov exponent. Yeah, Lyapunov exponent is zero, and so a priori you could think, okay, it can become positive or negative. But now, the theory based on phase reduction, so you now make the phase reduction, and you get one-dimensional noisy system, and in one-dimensional system, so the Lyapunov exponent can be only negative. You don't have in one dimension, if phase reduction works, you don't have any way to have positive Lyapunov exponent because just trajectories, so there is no, okay, so they cannot, it's just as in one-dimensional maps, invertible maps, yeah, so Lyapunov can be zero or negative, indeterministic, and this property is inherited by random maps. And yeah. So you can even make an exact calculation if you assume as a physicist so that this is some kind of white noise. Here, Lyapunov exponent is just, you have to average this. You have to find invariant distribution in one dimension. It's just, you write the corresponding integrals. For small noise, it is a strictly negative quantity minus epsilon square, this integral of this guy. So it means so that for periodic oscillators, weak noise always synchronizes. Yeah? It's just because there is no way. Now, if you go, now you can now take a little bit, make a more, how to say, analysis. I will not go to detail. You can say, okay, what happens if my two systems are not really identical, but are slightly different? What will I observe? So the answer is that now your, how to say, distribution will not exactly delta function, but some smeared distribution, which is looks like this. In the approximation of a small mismatch. And also, if you have a little bit two different noises, so here minus and here plus, then again you can find a distribution which is in the limit of this sigma goes to zero, it goes to a delta function. So there will be still two phases still stay close to each other, but of course, so they cannot be identical because there is some disturbing. The full symmetry is disturbed. Now, okay, here, yeah, okay, so there's a sigma, there is parameter sigma, which is plus here and minus here. So it is a frequency mismatch. And then I make, I assume so that these phases are close to each other, and then I linearize, and then we get such a distribution for the, you have sum and difference, and for the difference, you have such a distribution with this tail. So it means so that so distribution of their difference. So sigma is mismatch, and epsilon is noise. It is hidden in this Lyapunov exponent. Sorry, epsilon. It's only Lyapunov exponent is coming here, not epsilon itself. So in the leading term, so it's only Lyapunov exponent is coming. And Lyapunov exponent, it depends on epsilon. So this is the Lyapunov exponent, and this quantity is coming here. So it is epsilon square here. Epsilon square here. So your mismatch should be, okay, so you have to compare your mismatch with the Lyapunov exponent. Sorry?
F and F prime in front of
Here? No.
and F prime.
F is this, so this is how you define your system. It's a cosine function, some 2 pi periodic function of, it's 2 pi periodic function of, but from this function, it's only this quantity, how to say, matters.
F prime is equal to 0.
Yeah, there is nothing, so it is just, Lyapunov exponent remains 0. Now, there was a question, you see, so you can ask, if noise is small, it will be negative. But if it is large, can it become possible? The answer is yes. So if you have a nonlinear system with a periodic cycle, you add small noise, Lyapunov exponent goes to negative values, but it can become positive after for strong noise. So there is nothing prevents, and then it will be this property of synchronization will be lost. Now, there is some conclusion to this part. So Lyapunov exponent governs synchronization driven by common noise. You observe it for an ensemble, but not for one realization, and also desynchronization is possible. And now, as in the last part of the talk, I want to bring together these two effects, common noise, but also the coupling. So I will consider a Kuramoto model of so many coupled oscillators with common noise. So I a little bit remind you, because we'll need to go carefully in some notions of the synchronization, which we learned when we spoke about two oscillators or about Kuramoto model, because here they will have some, how to say, twist. So if you have just two coupled oscillators, so the phases come together if they are attractive, or go make a phase difference of the phases will be pi if they are repulsive. Of course, there are intermediate cases, but let us stick to these two. Now, if you think about, so in all cases, so the dynamics reduces to this Adler equation if you have two oscillators. Now, coupling is I call now mu. And you see, if you now look on frequency difference, you have in both cases synchronization in the positive coupling and negative coupling. Just here it is in-phase locking, and here it is anti-phase locking. But in both cases, the frequency will be the same. So you see, so this is this picture, so that if either mu is large positive or large negative, it will be, frequency will be the same of two oscillators. So you can say that for two oscillators, or altogether, you can speak about phase locking, so that the phase difference is a constant, so the phases go together. But you can also speak about frequency entrainment. So the two frequencies are exactly the same. And here it looks like that there is, between these two notions, there is no large difference. Yeah, because of course, if the difference is constant, so then necessarily it must be so that velocities are the same. Yeah? Average velocity. Now, if we go to the Kuramoto model, where we have many such oscillators coupled, so through the mean field with maybe some distribution of frequencies, then we have asymmetry between repulsive and attractive coupling. Because attractive coupling can bring phases together, but repulsive, it just leads to their distribution, uniform distribution. So previously for two, there was, in both cases, it was synchrony, and now not. So if now we have two quantities, again, we have phase locking and frequency entrainment. Now, phase locking, if we have many, how can we characterize it? We just characterize it with the order parameter. So if it is large, then the phases, we observe phases together. We say, oh, this is situation of locking, and this is not locking because they are distributed. Now, how we can speak about frequency entrainment? We can just measure their frequencies and look if they are close to each other or not. And for the Kuramoto model, these are these two quantities, this order parameter and the frequencies. You see, if I go to negative coupling, there is no any effect of frequencies just because there is no mean field. Okay, here there are some fluctuations of the order parameter because I take some finite ensemble, maybe of 50 oscillators. But for the positive coupling, the frequencies come close together, and eventually they are all have the same value. And order parameter is here large. So frequency entrainment here, so they come close together, and it goes together with phase locking. Yeah? So it is just what you expect. Now, so here I repeat this about common noise. Now you do this the same with the common noise. You put this common noise here, and you also want to see whether it is phase locking and frequency entrainment. And phase locking, again, I measure by this mean field, and it will be large because the phases I want to stay together. But what happens to the frequencies? Essentially, frequencies are not changed by common noise. Because you see, especially if it is white noise, so that the mean frequency of oscillators is not changed if you add noise. So if you now look on the same picture, so here's now noise intensity, you see so that phases are coming together, so you have a phase locking, but there is no any frequency entrainment. So they remain more or less parallel lines. So each oscillator has its own frequency. Yeah, I will give, the last slide will explain how it happened, but it is like this. And now, if we put two things together, there is an interesting effect. Yeah? So if I put common noise and attractive coupling, they both act in the same direction. So they both lead to large order parameter, and frequencies are pulled together due to attractive coupling. Common noise doesn't influence frequencies. So I have both phase locking and frequency entrainment. So frequencies come together, phases sit together. But if I have common noise and repulsive coupling, it is an opposite action of these two factors. So noise leads to a large order parameter. It brings, phases together, but they are repulsive, so they don't want to sit together. And their frequencies will be different. They will be even more different than they were without. So they are pushed apart, not pulled together. So I put here the following picture. So now the noise is fixed here, and there is a coupling. And you see, so here there are natural frequencies because they're only influenced by noise. And noise doesn't influence frequencies, and there is a relatively large order parameter. If I go in this direction, frequencies start to be pulled together, and the order parameter becomes even larger. So there are two effects which come together: frequency entrainment and phase locking. So phases are together and frequency are closer. But if I go here, okay, so order parameter will be smaller, but it's still large. It's somehow maybe 0.8 here. But you see, so the frequencies go apart, they are repulsed. Now, it looks as paradoxical, so we have some here theory-based, I don't know, equations. So there is, you see, so some even analytic solution, gamma functions, whatever. I'll just put here the picture. What happens? Now, this red curve, I just take in this population two oscillators and draw their phase difference. Phase difference, and I divide it by 2 pi. So this is 2 pi, 4 pi, 6 pi, and so on. Now, you see what happens. So this two phases, they mainly stay together. But then the first oscillator makes a slip relatively fast, and they again stay together, and again a slip. So they really have different frequencies. Although they stay together, so the phases are almost together, but because of the slips, the frequencies are different. If I put on top of this attractive coupling, it is this green curve. Then the slips are more seldom. So they longer stay together, and the slips are more seldom. So the frequencies, so the phase difference, so the frequency, average frequency is average slope of this curve. It is smaller than of the red one. But if I put repulsive coupling, they still, for a long time, stay together. Yeah? So you observe, so the two guys stay together, but they make more often slips than it was before. And so their frequencies are more, how to say, different than they were without coupling. So you see, you can have a situation where so in the ideal case, I would say, so they almost all the time they stay together, but nevertheless their frequencies could be completely different. So you have such a situation where can imagine so how it will with humans. So if they stay together, but then make this random phase slips, whatever is happening. Yeah. So this is the reason for this effect. Yeah. So that staying together and having the same frequency is not the same. You can stay together and can have completely different frequency. Yeah. So this is how this stochastics, how to say, influences this. Yeah. Yeah, so this is an example. So for me, it's the first time I saw this. So that these are, how to say, you have frequency phase locking, but frequency anti-entrainment. So here you see so that if you observe the two phases, most of the time they are close to each other. But the frequencies are different. Yes, yeah, but you see it is not real entrainment, because then it's, if Kuramoto parameter is 0, then the frequencies are like without any coupling. So they were already closed in the beginning. So there is no, how to say, influence of the interaction on them. Okay. So you see, so there is this phase locking and frequency anti-entrainment, they can be due to these two, how to say, ways of synchronizing oscillators. So I'm a little bit earlier, but maybe I'll stop at this point. Or I have some, but I'm not sure that there is some slides on some a little bit remote topic of synchronization of chaos, not of oscillators. But maybe it's not so interesting. And now you see, I would say, so the property that phase dynamics has always negative Lyapunov exponent is, how to say, it's topological, doesn't depend. And there was some theory based on some pulses, Poissonian pulse trains, which, yeah, and here, but here it is a theory based on white noise. I have not seen something about with correlated noise. I would expect only qualitative difference, but no quantitative difference, but not qualitative one. So here it is. What matters is so the Lyapunov is negative. Mm-hmm. Okay, so thank you for your attention.